So, there's a particular application of matrices to populations and things like that that change year on year. And it's a bit like differential equations where our time period is 1 year. Some of you will remember on Look Separately at the fox and rabbit type models. It's a bit like that we did in differential equations. Here we're going to have a look at it in matrices. And these are called transition matrices. Okay, so let's have a read of this example. There are adult and juvenile meerkats living in a population. Each year, so our time period is a year that they're modelling here. Well, we have a birth rate information, 20% birth rate per adult in the population each year. Adult survival rate is 90% each year. Juvenile survival rate is only 70%. You tend to use more juveniles. And of the surviving juveniles, the number that mature to adulthood each year is 40%. So what we can do is start off with how many adults and juveniles we have in a particular year. We're going to call those AN and JN, where N is the year. So A for adult, J for juvenile. And next year, that's going to be year N plus 1. We can find out and we can predict how many adults there'll be and how many juveniles from how many were at the start of the year. So let's have a look. Let's have a look at adults first. Well, adult survival rate is 90%. So if I take the number of adults last year, this year rather, AN, next year, 0.9 of them would have survived. Okay, so that tells me about the adults. What's happening with the juveniles? Well, they're telling us that 0.4 of surviving juveniles are going to become adults. How many of them survive? Well, 70%, so 0.7 of last year's juveniles, this year's juveniles. So what have we got there? Well, we've got 0.28, and that's 0.4 times 0.7 of juveniles will become adults. Of this year's juveniles will become adults next year. Okay, let's have a look at what's happening with juveniles then. How are they affected by the number of adults? Well, we've got births, and it tells me that 0.2 times the number of adults. So next year there'll be additional juveniles dependent on the number of adults this year. And what do we know about survival rates, etc., for how many of this year's juveniles are going to be around next year? Well, it's telling us that 0.7 of them survive, 70%. 40% of them become mature adults. That means 60% of them are left. So that's 0.6 for that. And 0.6 times 0.7 is 0.42. So here we have simultaneous equations here going from this year to next year. And I could rewrite that in matrix form, couldn't I? Because my population matrix vector, for next year is AN plus 1, JN plus 1. My population vector for this year is AN, JN. And I've got a transition matrix T. And that's going to have, well, what we're going to have in the top left corner? Well, it's 0.9 AN. It's 0.28 JN. There we go. That's the number of adults. And then if we look at the number of juveniles, it's 0.2 juveniles, so adults, and 0.42 juveniles. So I've now got a transition matrix. That's called a transition matrix between what's happening this year, population, which I'm going to just call vector Vn, and this one here is my population, and V is N plus 1. So there we have a nice simple relationship. You'll notice that we haven't got any other extraneous or third factors like food or anything like that, which we can build into diff equations. Here we've just got a population to population. This is a very popular question with Edexcel. Okay, so what does that mean I can do with this? Well, if I know my initial population, I'm going to call year naught. I'm going to call this V naught. If I knew that I had 1,000 adults and 200 juveniles, I could multiply by my transition matrix, and I'd know what the population is next year. If I do that calculation using my calculator, I get 956 adults, 284 juveniles in year 1. How many would there be in year 2? Well, I could take my year 1 figures and multiply it by the matrix, and I'd get my year 2 figures, population figures. 939 adults, 310 juveniles. Now, those of you might have just thought, oh, well, I didn't need to do that, because what I could do is just take my initial, I didn't need to do it as a two-stage process. I could, to get to the year 2, I could have taken my initial population, multiply it by t squared. I agree, and that would have given you V2. So that gives us much more flexibility, doesn't it? Because if I want to get to the population in Vn, all I need to do is take my transition matrix t to the n, and multiply by power n times, and multiply by my initial population. Well, if I wanted to know the population the year before, so if this is year V naught, what if I wanted to know what it was in V minus 1, a year before? Well, rather than multiplying by t, I've got to multiply by its inverse, t minus 1. And of course, we've all got lovely calculators to do this, haven't we? Our calculator will work out the inverse matrix, there it is, and I multiply those out and I get my V for negative 1 year minus 1 as being 1,130 adults and negative 62 juveniles. So that's not particularly realistic because we can't have negative populations. But the principle is made that this is how we can use them. So there we are. In summary, we have a relationship that looks like that. Whatever it is, population vector for year n plus 1, it's just going to be transition matrix times the population vector for year n. So setting it out here, classic example there, the example I've just used. If I know my initial values, I can find year 1 and year 2, and of course I could find year n by just doing my transition matrix to the power tn. And if I want to work backwards, then I'm just going to multiply by the inverse of the transition matrix. So that gives you an introduction. We're going to have a look in a bit about how it works in practice, how it might be useful with invariant lines.